my name is Chris Harris and I'm from Allery Chemistry, and this video is going to be on equations and inorganic chemistry. So the whole point of this video is basically to bridge the content that you've learned at GCSE to the content that you're about to learn in A-level. So it's designed to bridge the gap between the two, because the gap can be quite a big gap between GCSE and A-level. So like I say, they are designed to link the two together, because chemistry is probably one of the most demanding subjects at A-level, so sometimes it requires a little bit of help. So this video is designed to do that. There is a lot more videos on A-levels. There's quite a comprehensive range of A-level videos on Allery Chemistry YouTube channel, so go and have a look on there for the full A-level. But what I've also done as well with this video is I've done a series of questions, and they're multi-choice questions. They're all online, so you can access the questions, complete them, and it will actually answer them straight away. So if you just click on the link in the comments box just below, that will have all the information that you need. So you click on that link and then you can get access to that quiz. And it's designed to test your knowledge on the content, to see if you've learned things. Because some of the stuff you'll see on this video, you will have seen at GCSE, and some of it will be a little bit new. So it's designed, like say, to bridge the gap and give you a little bit of a head start. Okay, so let's look at the first one, which is equations. And you would have seen these at GCSE, and these are quite important for chemistry because chemistry's got a lot of equations in, but equations come in different forms, as you're going to see here. So an equation has two main types. You've got a word equation, which contains words, and symbol equations, which contains chemical formula. So both are used. The symbol one's more difficult than the word one, but you need to know both. So let's look at the constitution of an equation. So an equation has two parts. You've got the reactants on the left-hand side, and then you've got products on the right-hand side. And sometimes you'll see some substances in these equations where they're actually written above or below the arrow. Normally these are catalysts. So for example, if you've got a reaction and it needs a catalyst for it to react, because the catalyst doesn't actually get used up within the reaction, we normally find it above the arrow. So you might see that. Or sometimes it might be reaction conditions such as reflux, for example. It might be distillation. It may be the temperature that we operate this at. So you'll see that again quite a lot in A-level. So the word equation is basically, like I say, it has words in it. So we've got ethanoic acid, for example. In this example here, we've got ethanoic acid plus ethanol will form ethyl ethanoate plus water. So this is the formation of an ester, which you may have seen at GCSE. Don't worry if you haven't, you will see it a lot more at A-level anyway. So a word equation is fairly straightforward. A symbol equation, like I say, contains the chemical formula of the words that we used in the equation before. So, for example, the symbol equation for the reaction we've seen there is CH3COH. This is a carboxylic acid. This is ethanoic acid. This is ethanol. This is ethyl ethanoate, which is your ester, and you produce water as well. So this just shows the formula there. Now, you will need to balance these as well. Balancing equations is very important. So this one's balanced already, but there are some where you may need to add numbers in front. But we'll look at that later on about balancing, because that's just as important. So that's what I was saying there. So you put the numbers in front of the substances to balance it. Okay, so balancing equations, we need to be methodical. Balancing can be quite tricky, but really all we're looking at is you've got to have the same number of atoms on the left and types of atoms on the left as you have on the right, and it's as simple as that. However, in practice it can be a little bit more tricky. So you've got to be methodical and check regularly, constantly check how many carbons have we got on the left, how many carbons have we got on the right, how many hydrogens, etc. So we're going to look at in this example, the combustion of butane. Now, butane is camping gas. It's normally used to get in these metal cylinders, as you can see here. Normally used for barbecues, heating, sometimes used in patio heaters. So, they're used quite regularly as a fuel. So we're going to look at the balancing of this equation. So the first step we have to do is write out a symbol equation. So in this case, methane is C4H10. Again, you might have seen this at GCSE. This is nothing too unusual. Methane is C4H10. Oxygen, because when we burn anything, combustion is just a reaction with oxygen. Carbon dioxide and water. So the next step is we then need to work out how many of each element we have on the left and how many we have on the right. But the key thing with balancing equations is we cannot actually change the formula. We must put a number in front of each of the substances there to balance. We can't actually change the actual formula for it. So let's start. So on the left-hand side, we have 4 carbons on the left. So we need to have 4 carbons on the right, basically. So to balance this out, we put a 4 in front of CO2 because that's the only substance on the right that contains carbons. So if we need to balance carbons, then that's the only way we're going to be able to balance it, because there's no carbons in water, obviously. The next one is that we actually have 10 hydrogens on the left because we've got C4H10. So we need to have 10 hydrogens on the right. And again, the only substance on the right-hand side which contains hydrogen is water. So we need to put a 5 in front of there because 5 lots of H2O gives us the 10 hydrogens that we need to balance it out from the left. So we need to keep going because it's still not balanced. So we have 13 oxygens on the right-hand side because we've got 4 lots of CO2, which gives us the 8 there. And then we have 5 over here because we've got 5 H2O. So oxygen is a little bit more difficult to balance because we've got oxygens in both substances here. So we need to put 6.5 in front of that. So effectively 6.5 times 2 gives us 13. So you can have half moles. Now GCSE, you might not have seen it where you've written, if you've been balancing equations, you might not have seen it where you've put a half number of moles, but they do exist, and there's nothing abnormal about that at all. And this case, we've got 6.5 O2. That gives us the 13 oxygens that we need on the left-hand side. So don't be too alarmed if we see half moles for balancing equations. That's perfectly normal. Okay, so ionic equations. So this is where it gets a little bit more complicated. Similar process. We still have an equation, still needs to be balanced. We still have our elements and substances in there. The only difference here is that ionic compounds, we can break them up into the constituent ions that make up that compound, and we can balance them out. So this is basically just showing you how we can write an ionic equation. Now you might have seen this at GCSE, in particular if you've looked at extraction of aluminium, so electrolysis, you might have seen ionic equations there, or half equations in fact with electrons. So you might have seen a little bit of this at GCSE. At A level, you're going to see a lot more of it, unfortunately. So this is designed to kind of bring that knowledge from GCSE to A level. So we've got a balanced equation here, and this is an acid reacting with a base. So in this case, it's sulfuric acid reacting with, this is sulfuric acid here, reacting with potassium hydroxide, and that'll form potassium sulfate and water, so that's salt plus water. So what we can do is we can split these components up into their ions if we can. So H2SO4 can be broken up into H plus and SO42 minus. Now you would have seen in the previous video about ions, molecular ions, so you need to be quite familiar with them, and you need to know that SO4 is a molecular ion, and so that is SO42 minus. Now we have 2 lots of H plus because we've got 2 in this molecule here, so that's split up there. Potassium hydroxide, exactly the same, we can split that up. So we can have K plus and OH minus. There's another molecular ion that you need to be familiar with. Because we've got a 2 in front of there, we have 2 lots of each. So we have 2 K pluses and 2 OH minuses. Potassium sulfate is another one. So K2, because we've got 2 potassiums there, that's 2 K plus. And SO4, that's SO42 minus. So you can see that all these charges, they balance up to form a neutral compound. Water isn't an ion, so we just leave it as it is. So anywhere we see water, you just leave it. So in this case, it's just H2O. Okay. These ions as well, that's not quite a good point. Again, you'll see this a lot more in A level, but most ions exist from acids, bases, and salts when they're dissolved in solution. That's normally where we see ions being formed. Because this is an acid and a base, and this is a salt, they dissociate, it's the word we use, where they break up into their ions. So what we need to do, because we've got the ions, we've expanded this equation and brought in the ions. We need to cancel any ions that exist on both the left and the right because they cancel out, and we simplify this ionic equation. So this is what we're going to do now. So there we are. So what we've done is we've cancelled out the sulfate ions and the potassium ions because they exist both left and right, and we get our simplified equation, which is 2H plus 2OH minus will form 2H2O. Or in other words, H plus OH minus forms H2O. So this is a classic simplified ionic equation for the neutralization of an acid and a base, a neutralization reaction. So what happens with SO42 minus and K plus, these are known as spectator ions because they do exist, but they don't play an integral role in the actual reaction. So we call these spectator ions. They effectively watch like a spectator. They just watch the reaction happening. The final ionic equation must balance. So you can see here that it does. We've got 2 hydrogens there, that's 4 hydrogens. That means we've got 4 hydrogens there, and we've got 2 oxygens, and again 2 oxygens there, so it must balance still. You might see state symbols as well. State symbols are quite important because it tells us what physical state the substance is in at room temperature. So you would have seen these before, I would imagine, at GCSE, but just as a reminder, S is a solid, L is a liquid, G is gas, and aqueous is AQ. You'll see this quite a lot actually at A level is AQ. That's basically anything dissolved in water, in which case anything that's dissolved in water can be split up into its ions. So look out for them. Sulfuric acid is dissolved in solution, and so is potassium hydroxide, and so is that. Water is clearly a liquid, so that doesn't split. So that's a key thing. Look for aqueous, wherever you see AQ, and you can split them into ions. Okay, so pH. Now, you definitely would have seen this at GCSE. pH scale, just as a reminder, it runs from 0 to 14, and it tells chemists how acidic or basic something is. And that's quite important because we need to be able to identify what type of substance has been formed, because that can then lead us, or what type of substance we're dealing with, because that can then lead us to handle it in the particular way. So for example, if we know something is pH 1 or pH 0 that's highly acidic, we've got to treat it with care, particularly if it's quite concentrated, because it can cause quite nasty burns on the skin and blistering or even irritation. And likewise, if it's alkaline as well, we've got to treat it with the same level of precaution. So we use different we use numbers to basically decide if something is acidic, basic, or neutral. So we start at the far end, 0. So 0 or 1, stomach acid is classed as a strong acid. It's hydrochloric acid in the stomach, and it's purely there to allow enzymes in your stomach to do their job. So remember, if you've done biology, it isn't the acid that actually breaks down the food, it's enzymes. But these enzymes prefer acidic conditions, so that's why the stomach acid is in there. Weak acids are things like citrus fruits, so you'll get things like citric acid in lemons and limes and oranges, etc. So these are still acidic. You'll know if you obviously taste it, it's quite tangy, but it's not as strong as stomach acid. Neutral is pure water, so that's a relatively straightforward one. Weak alkalines, things like soap. So soap, like bars of soap or even liquid soap in hand dispensers. So they are classed as a weak alkaline. So they're good at killing germs and killing viruses and bacteria. And if you wash your hands quite regularly with these types of soap, it'll dry out your skin. So alkali, you're getting an effect of an alkali there. Obviously, it's dissolved in water, of course, but increased exposure to alkalis effectively dries out the skin. So it has a slightly different effect to acids, but still not pleasant. And the strongest alkalis are things like drain cleaners and oven cleaners. And if you ever have used or get in contact with strong alkalis, you know that they look like syrup. They're quite thick, and they're really, really nasty if you get them on your hand, just like a strong acid. So, but they're great for removing stubborn stains, for example, things that are baked in or ingrained in on surfaces. Alkalis are really good at lifting that off. Okay, so let's look at some acids, bases, and alkalis. Acids are proton donors, so you may have seen this as well at GCSE a little bit. This is just going to expand on it a little bit more. Bases are proton acceptors. So when we have acids and bases, they're dissolved in solution, and they actually exist in a reversible reaction. So that means the forward reaction and there's a backward reaction. So there's two types of reactions here. So for an acid, we can represent an acid as HA. That reacts with water because acids are dissolved in solution, and so that forms something called H3O plus and A-. So this is just the bit from the acid, whatever that was attached to. That could be a sulfate, it could be a chloride, it could be a nitrate, it could be anything that's bonded to that. Will break off here. Bases, very similar, except it's a base. Again, that's dissolved in water as well. Bases are dissolved in water, and they form BH plus and OH-. So the key thing here is that an alkali, the difference between an alkali and a base, and you may not know this from GCSE, but it is worth, because the two words are thrown around and they often get confused, but an alkali is just a soluble base. So they all produce OH-. Alkalis produce OH- in solution, and it's that what makes it basic. So acids, what makes a solution acidic is if it's got H plus ions, an excess of H plus ions in solution. What makes something basic is if it's got OH- ions in excess in solution. So that's the main difference. Now you might see this, acids produce H3O plus for simplicity, and you will see this, and you've seen that in GCSE, but in A level it's the same. We just write it as H plus. It makes it so much easier. So wherever you see H plus, that means it's acidic. There's an acid in there. Okay, so let's have a look at some of the different types of acids and bases that we've seen. So a weak acid, classic example is ethanoic acid, carboxylic acid. You'll see a lot more of this at A level. You might have seen some at GCSE, but you see a lot more at A level. The extra information, weak acids, effectively, the backwards reaction is favoured. If you've done reversible reactions at GCSE, which you may have done, then you'll know that when you've got a reversible reaction, you've got a forwards and a backwards reaction. Now, for a weak acid, effectively, we've got loads of the reactants. We haven't got much product. And remember, it's this that makes it acidic. If there's not much of this in solution, it's not very acidic. So weak acids, as you can see here, weak acids actually have, if you had a beaker of this in water, most of that beaker would contain this and not much of this. And that's what makes it acidic. So that's why they're weak. Now, if we contrast that with a strong acids are things like hydrochloric, sulfuric, nitric acid. These are strong acids. This is the opposite. So when we drop that acid in water, acids break up into their ions. This acid, strong acids, actually break up very readily. So you get loads of H plus ions. If you had a beaker, you would get the majority of that beaker will contain these ions here, and you won't get much of this because it's favoured much more to the right hand side. Strong acids dissociate really readily. In other words, they break up very easily. Weak acids don't. Okay, very similar, strong bases. So strong bases are things like sodium hydroxide, potassium hydroxide. These are strong bases. So these are the ones that use an oven cleaner, for example, and drain cleaner. Again, the forward reaction is heavily favoured in strong bases, just like strong acids. So, for example, sodium hydroxide is the base that breaks up into Na plus and OH minus. That's what makes it basic. And then weak bases, there's only one example you really need to know here, which is ammonia. Ammonia is a little bit weird because it doesn't actually have OH attached to it. So you'll notice that NaOH, KOH, that's a classic sign that it's a base if it's got OH attached to it. But ammonia is an example where it doesn't actually have an OH. And what it does is it actually uses water here to create an OH minus, because for something to be basic, it must have OH minus ions in solution. So ammonia uses water to produce the OH minus ions, so it's kind of by proxy rather than actually breaking up directly. The same reason though why strong bases are strong bases and weak bases are weak, because they don't dissociate very well. So ammonia doesn't really produce many OH minus ions, and that's why it's a weak base. Okay. So these are the two. These are all the two different types. You've got acids and bases, and obviously how they're broken down too as well. Okay, so acids react with bases to form salts, and they're pH neutral. So you'll know this from GCSE. You'd have definitely done these reactions. So the H plus ions that's produced from acids, they can react with the OH minus ions produced from alkalis, and when we react these two together, we form water, which is in neutral. So a good example is this one here. So we've got hydrochloric acid plus lithium hydroxide. So this is a base because it's got OH, look, and this is an acid. And if you remember, this is a strong acid, strong base. This will form lithium chloride, so LiCl, and H2O. So notice we've got AQ, AQ, AQ. So these are all dissolved in solution and liquid. So anything AQ, we can split these into ions. So salts are made from the metal from the base. So in this case, there's the metal from the base, lithium, or ammonium, depending on what it's reacting with, and the non-metal of the acid. So this is the non-metal here, the chlorine from the acid. So it's the metal and the non-metal, and that forms the salt. So that's how you know what salt's produced. So in this case, it's lithium chloride. So if we look at another one, this is nitric acid. That's a strong acid. Against potassium hydroxide, that's a strong base. Then we form potassium nitrate and water. So there we are. So we form our salt plus water. Again, we're taking the non-metal bit from the metal bit. What we've got to be careful of is ammonia. Because we know that ammonia doesn't produce OH minus ions directly, what it does, like we said before, it reacts with the water first, accepts a proton, produces ammonium ions, and then produces the OH minus ions. So it's because ammonia itself doesn't have an OH like these ones. So it needs to use water to produce the OH minus ions. Okay, so ammonia, that reacts with acids to make ammonium salts but it doesn't produce water. So you've got to be very careful with that. So for example, there's ammonia reacting with sulfuric acid, and that forms ammonium sulfate. Basically, it forms one big salt with no water produced. It's still neutralization because we're forming a substance which has no acidity at all, but it's just a little bit different, so just be aware of that. Okay, so let's look at some group 2 elements. So because this is inorganic chemistry, you would have looked at organic chemistry in at GCSE, and you would have also looked at inorganic. So inorganic is basically anything which doesn't doesn't evolve around carbons and hydrogens, so hydrocarbons. So these are things like group 2 metals, group 7s, transition metals. They're classed as inorganic. So this bit, we're going to look at group 2 and group 7. So we're going to look at group 2 first. So group 2 elements, they all form +2 ions when they react, and they form them by losing 2 electrons from its outer shell. And you would have seen this before. You would have done ionization. There's a video, I believe it's video 2, that contains information about ions and ionization, and video 1, definitely video 1 it's video 1 that contains the ions. So this is just building up from that. But group 2 forms +2 ions, and the reactivity increases as we go down the group. They become more reactive. And there are a few factors that affect reactivity, and one of them is atomic radius. And basically, and you would have seen this again, definitely in video 2, you would have seen this as well. But if you haven't seen that, then basically, the larger the atom is, the further away the outer electron is from the nucleus. And remember, the outer electron is attracted to the positive nucleus in the middle. Now, if that electron is further away from that positive nucleus, then the force between them is a lot weaker. And so therefore that electron is lost much more readily. If it's lost much more readily, then that means it's more reactive. Now, as we go down group 2, the atoms get bigger. So because they get bigger, the electron's further away from the nucleus, it's lost more readily, and therefore it's more reactive. And that's why group 2 metals are more reactive. So that atomic radius increases as we go down group 2. So we can see this here in graph form. So we've got some group 2 elements starting from beryllium to barium. So there it is there. So you've got beryllium, magnesium, calcium, strontium, and barium. So beryllium has the smallest radius. It is the smallest ion. And then as we go down the group, that atom gets bigger. Okay. So let's look at ionization energy. So remember, this is where we are removing, it's the amount of energy required to remove an outer electron from an atom. Now, as we go down group 2, we know the atom gets bigger, but what we also get is we get extra shells between the positive nucleus of the metal and the outer electron. Okay, so we have more shells between the positive nucleus and the outer electron. That's called shielding. And the more shells we have between that, the weaker the force is between the positive nucleus and the electrons on the outer shell. So we get extra shells added, and that has a massive impact on how easy it is to take the electron. So let's have a look. So we've got more shielding, like I say. So that means we get a weaker attraction between the nucleus and the outer electrons. And so the outer electrons are further from the nucleus, and this weakens the attraction. And so both of these factors make it easier to remove the outer electron, so less energy is required. So we can see from this graph here that we have the ionization decreasing as we go down group 2. So going from beryllium to barium. Now we do have an increase in the number of protons, so as we go down group 2, we've got more protons in that nucleus. And you might think, well, surely that should, because you've got more protons in the nucleus, you've got a bigger charge, and so therefore that should hold these electrons in more readily. It does to an extent, but the shielding overrides that positive charge. The fact that, and again, it's a bit like having 2 bar magnets. If you put a bar magnet quite a distance away from each other, you don't really feel the attractive forces that much, but if you pull the bar magnets closer together, the forces you feel the force of the magnets sticking together a lot more. This is a similar principle. You have electrostatic forces between the positive nucleus and the outer electron. But if we have a lot of things, or a lot of shells between that, which is the shielding, that's going to weaken it. That's like putting numerous bits of paper in between 2 bar magnets. If you put a lot of things in the way of the 2 magnets, the force is going to weaken. So it's not going to take a lot of energy to pull them apart. Okay, so let's look at their reaction with water, because this is a key thing about how group 2s react. So Group 2s react with water to form bases, and the reaction with water forms metal hydroxides. So you can see here we've got a group 2 metal, which is strontium, reacting with water, and it forms strontium hydroxide and water. So that's what they form. So the reactivity, again on the basis of them, the rules that we mentioned before, the reactivity increases from beryllium to barium. And in fact, there isn't a reaction with beryllium. It's so difficult to remove that electron from the outer shell in order for it to react with water that there is actually no reaction. But the ones further down the group do, and they form hydroxides. The atom gets larger, as I say, the electron's further from the nucleus. It's easier to remove that electron, and because there's more shielding, which weakens that attraction. Magnesium. Now you might have seen this. Magnesium's that ribbon. If you put it into a flame, it burns really brightly with a really bright white light. You shouldn't stare at it directly because it can damage your retina. But magnesium reacts slowly with cold water. So if you put a bit of magnesium in water, it doesn't really do a lot. But it reacts much more vigorously with steam. So if you push it in steam, it actually produces magnesium oxide. But don't worry too much about that. You'll know a lot more about this at A level. Okay, so melting points for group 2. Melting points generally decrease as we go down the group. So group 2 elements, they form metallic structures, and you would have seen that in the video 2, which is on bonding. They form metallic structures, and so what that means is you have your positive metal ions and you have a delocalized sea of electrons, and that attractive force between the positive metal ions and the delocalized sea actually provides the metallic bond. But if you look at video 2, that's got a lot more information on metallic bond in there. But basically, as we go down group 2, the size of the metal ion increases quite significantly as we go down, but the number of delocalized electrons remains the same. It's +2 because each group 2 element produces 2 electrons, but the size of the atom actually increases. Now what that means is these larger ions means that the distance between the positive nuclei and the delocalized electrons is much greater, and because we've got a greater distance, that weakens the force. And what this means that it's easier to break the bonds, and hence less energy is required when we're trying to melt it. So this leads to lower melting points. So we can see here from beryllium going down to barium, the melting point decreases. There's a little bit of an exception, which is magnesium there, but this is due to the structural arrangement of it. You don't need to worry about that at A level. It's just a case of you need to know the general trend. Okay, so let's look at group 7s because they're part of the inorganic chemistry arena as well. So the halogens make up group 7 of the periodic table. So the first one, if you look at the periodic table, group 7 is towards the right hand side. The first one's fluorine, and it's a pale yellow gas at room temperature. Chlorine is a pale green gas. Bromine is a browny orange liquid. It's one of the few elements that are liquids at room temperature. The only one which is liquid at room temperature is mercury. So bromine's quite unique in that fact. And iodine is a grey solid. You may have seen some of these at GCSE, in reality. So for example, you might have seen bromine water, and you might have seen iodine. So the boiling points, as we go down the group, the boiling point increases. And this is because the intermolecular forces increase because the size of the atom increases. And again, we looked at intermolecular forces in video 2. So if you're not quite sure on what that means, then have a look at video 2, and that goes into intermolecular forces into a lot more detail. But the size of the atom increases, therefore we've got higher intermolecular forces. And so the physical state goes from gas at the top to solid at the bottom, as you can see. These are at room temperature. And from a bonding point of view, halogens form covalent bonds. Again, in video 2, there's a lot more to do with covalent bonds if you're not familiar with it, so I encourage you to look at that. But they form covalent bonds. That means they're sharing electrons. Each atom in here is sharing electrons with the other atom, so therefore will form a covalent bond. They can form ionic bonds as well. So, for example, if any of these halogens are reacting with a metal, such as a group 1 or group 2, then halogens form negative ions. So they can lose an electron. Sorry, they can gain an electron from a metal that's donating it. So they can form ionic compounds as well. So they're quite versatile. So the reactivity. Basically, they become less reactive as we go down the group. So this is the opposite to group 2, but the explanation is the same. So as we go down the group, the atomic radius increases as we go down, and you can see that there. So what this means is that the distance between the nucleus and the outer electrons becomes larger, okay? and so there's more shielding. So the attractive force gets weaker as we go down the group, and this means it's less able to attract electrons. Group 7 elements attract electrons, not give up electrons. So because they've got 7 electrons in their outer shell, they only need 1 more to get a full stable shell. So it's much easier for group 7 to accept an electron than to lose the 7. So this is the opposite way to group 2. Okay, so that's very, very important, but the rules are the same. So we're still applying the same principles. So even though that nuclear charge, again, is exactly the same, as we go down the group, the number of protons in that nucleus increases, the nuclear charge increases, and this means that the shielding effect outweighs the increased positive charge. So even though there's more protons, you might think, well, that's going to attract them electrons much more readily. The shielding outweighs that completely. So, but it is an important point to note, because you are required to know that, but it doesn't have an impact. Okay, you might have seen these again at GCSE, which are displacement reactions. So displacement reactions are where we are reacting halogens, so halogen-based compounds and halogens together. And the general rule, as you may have seen at GCSE, is the more reactive halogen will displace a less reactive one. So displace just means to swap or exchange. So we know about the reactivity of halogens. So remember, the reactivity decreases as we go down group 7. So for a reaction to occur, an electron is gained. So remember, any reaction in chemistry is to do with electrons being moved or exchanged or gained or lost. Okay, so atoms with a smaller radius, these will attract electrons better than a larger radius. Okay, because the shielding isn't there. There's less shielding in smaller atoms. So the more reactive ones are at the top of group 7. That's your fluorines and chlorines. The least reactive ones are things like iodine and bromine. So these are the ones towards the bottom. So a halogen will displace a halide from solution if the halide is lower in the periodic table. Okay, so let's have a look at these. So if we're reacting chlorine, so the addition of chlorine, so we've got potassium chloride solution, we're going to react it with chlorine, then because these are both the same reactivity, there's no reaction. So that's fairly straightforward. The next one is potassium bromide and chlorine. Now chlorine is more reactive than bromine because it's higher in the reactivity series. Higher in the reactivity series, but it's higher in group 7. Then we do get a reaction, and effectively chlorine displaces the bromine from the bromide from potassium bromide. So we get a reaction, and this is the Ionic equation. So it's chlorine plus 2Br will form 2Cl minus and Br2. So we get an exchange. Effectively, we get potassium chloride, which is here. Obviously, the potassium is not shown in here because it's a spectator ion, but we form bromine. Same here as well. So chlorine is also more reactive than iodine, so we get a displacement reaction. And what we've seen is we get a brownie solution of iodine being produced, so a brown solution there. And here we get a brown solution, like an orangey colour, orangey brown, because that's bromine. So we can see a colour change, and you would have seen this at GCSE as well. Okay, so let's look at this one. So here we're going to add bromine water to potassium chloride, but potassium chloride is more reactive than bromine, so bromine doesn't have a chance. So they get no reaction, basically. Bromine and potassium bromide, these are just as reactive as each other, so there's no reaction. And finally, bromine is more reactive than iodine, so therefore we do get a reaction. So we get exactly the same colour change as we did for this one here. The bromine solution, brown. You get a brown solution being formed. It's because we see iodine being produced. Okay, and finally, now this has got no chance really here, but iodine reacting with potassium chloride, iodine's a lot less reactive than chlorine, so you get no reaction. It's a lot less reactive than bromine as well, and obviously it's equally as reactive here with iodine. So iodine reacting with potassium iodide, you're going to get no reaction. So you don't get many reactions with this, but it's all to do with which one is more reactive. So it's like halogen top trumps. Okay, and that's it. So that was just an overview of inorganic chemistry and the equations that's required for A-level. Like I say, there's a full range of A-level chemistry videos on Allery Chemistry, a YouTube channel, so go and have a look and go and subscribe. And also there is some questions relating to this PowerPoint here as well in this video. If you click on the link in the comments box, you'll be able to get them there. All right, that's it. Bye-bye.